So now we are going to observe the reflection by plane mirrors. Here I have a plane mirror attached to a stand so that it is easy to handle the plane mirror. And then I have the markings of angles and the line to place the mirror. So on this, if I place the mirror here, so you can see this is marked as 90 degrees, that is 90 degrees to this principal axis. So I can send a ray along the principal axis as well as I can send it along different angles. To generate the ray, I have a laser pointer here. So I will explain each ray and how it reflects. So here if we place the ray coming from the light source is the incident ray. And if the incident ray comes at an angle of 90 degrees to the plane mirror, here you can see that is along the normal line, you can see it gets reflected through the same path. So there is only one path there. Both the incident ray and the reflected ray are on the same line. That is when the angle is 90 degrees to the plane mirror. Now I will move the incident ray to a certain angle. Now can you all observe the reflected ray? Here you can see this is the incident ray and the ray that is coming from there is the reflected ray. And the line perpendicular to the mirror is the normal. What does the first law say? Law of reflection. Incident ray, reflected ray and the normal are all on the same plane. That you can observe here. What is the second law? Angle of incidence, that is this angle, is equal to the angle of reflection. So here you can see this angle and this angle are equal. So that is the second law. What will happen if I decrease the angle? Can you see the angle of incidence has decreased and the angle of reflection also has decreased. If I increase the angle of incidence, now you can see the angle of reflection also increases along with it. So from this observation, you can clearly understand that the angle of incidence is equal to angle of reflection. And also the incident ray, the normal and the reflected ray are all on the same plane. So now I am going to do a simple activity to observe one of the properties of the image formed by a plane mirror. You know what lateral inversion is. When you raise your right hand in front of a plane mirror, it looks as if you are raising your left hand. So that is what lateral inversion is. Here I have got a word written on this piece of paper. The word is ambulance, but you can't read it clearly. But when I hold it in front of a plane mirror, you will be able to see it the proper way. This is what they do in normal ambulance. So here when I turn it towards the mirror, can you see the letters clearly? Is it clearly visible to you? Yes, you can read the letters, the alphabets clearly and you can understand the word clearly. So this is a use of lateral inversion in day-to-day activities. Okay students, so now we are going to observe the type of curved mirrors or spherical mirrors. You all know there are two types, the concave mirror and the convex mirror. So here if I take this mirror, you can see it is curved outwards. So that means it's a convex mirror. And if we take the other one, This is curved inwards. So this surface is the non-reflective surface. The other side is the reflective surface. So here it's curved inwards. So it is a concave mirror. And you all know with these two mirrors, the way the image forms differs. Through one mirror, you will see a smaller image, diminished image, and through the other mirror, you will observe a larger or enlarged image. So now I have two pen lids to show you all how these images are observed through the curved mirrors. So if I hold the mirrors together, side by side, you can see the objects. Here you will be able to see the objects. One is larger. In one mirror you can see the larger image, and in the other mirror you can see the smaller images. So in the concave mirror you see the enlarged image, and in the convex mirror you see the diminished or the smaller size image. Can you all observe it clearly, students? Yes. So this is how we have the images formed in curved or spherical mirrors. So students, you can see the parallel beam of light here, and if I place the concave mirror in front of the parallel beams, you can see that all the beams are getting converged onto one point. Now to find the focal length, I will move the concave mirror back so that it focuses on this center point. So here you can see the focal length is about 10 centimeters there. So this is how all the rays focus onto one point when they are reflected by a concave mirror. Okay students, you can see now how convex mirrors reflects a parallel beam of light. You can see here the beams are being diverged. So they are not reaching one point, they are going away from each other. So they are being diverged. So this is a diverging mirror. You can observe that clearly. So here you can see students a ray coming along the principal axis. That is what I have shown here. If we place the concave mirror, now if I turn it, you can see that it is being reflected. But when it is along the principal axis, you can see it is reflecting along the principal axis. That is the first type of ray reflected by a concave mirror. So here students, you can see first the ray that is coming parallel to the principal axis. You can see it reflects and goes through the focal point. Now to confirm that it is going through the focal point and it cuts across the principal axis, I will include another ray. You can see the first ray is the parallel ray that is over this side, that is going at an angle through the focal point, whereas the ray coming along the principal axis is reflected along the principal axis itself. So they both meet at the focal point. If there were more than two parallel rays coming from both sides, now you can see all the rays converge onto the focal point. So here you see two parallel rays on either side and the ray going through the principal axis. This is how the rays meet at one point or converge at the center point. Okay students, initially we observed that the focal length of this concave mirror is 10 centimeters. So I have the focal point here, and if I want to get 2C, if I need to get C, that is at 20 centimeter mark, that is this point. So now if I send a ray through this So here you can see the ray coming through the center of curvature, that is 20 centimeters from this mirror, concave mirror, and you can see that it is reflecting along the same path. If I move the mirror like this, you can see the ray going along the same path. So a ray coming through the center of curvature reflects through the center of curvature. So now we are going to do this activity to determine the focal length of a concave mirror. So here I have is a concave mirror. You can see it's curved inwards, that is the reflective surface, and this side is the non-reflective surface. So you can see the concave nature of this mirror. Now this is what I am going to do. I have a screen here, then I have a stand for the mirror, but before I place the mirror on the stand, what I will do is, now I have set the screen so that I can get a reflection from the window onto the other side. So I will try to get a clear image of that scenery outside the window onto this screen. So if we can get the image on the screen, what do we call it? It is a real image, and you will see the image will be upside down. So that is an inverted image. So what we are going to get on the screen is going to be a real inverted image. Now I'll try to fix it onto this stand so that it's easy for me to handle it. I can easily adjust it and push it here and there. So now I have it a little far away from the screen. I'm moving it towards the screen. Now you can see the image, not clear enough, but when I bring it to a certain point, I think you can see the clear image now. So at this point, we keep the mirror at the point, and then we have to measure the distance between the screen and the mirror. So if I get the distance here, so it's almost around 10 centimeters, the length between the screen and the concave mirror. So that is how we measure the focal length of a concave mirror. Okay students, so now we are going to observe the images formed by a concave mirror. So here I have the concave mirror. You can see it's curved inwards, and this side is the reflective surface. This is the non-reflective surface. So therefore this is a concave mirror. And I have the stand here. I have told you all there is a mark at this point so that it is in line with the mirror. So we can easily place the positions the mirror at different points. So here the candle is the object and I have the screen there. So in the previous activity, we determined the focal length of this concave mirror as 10 centimeters. So here you can see the candle is at 0 mark and the mirror is at the 50 centimeter mark. So that means I have placed the candle 5 times the distance of the focal length. Now what I am going to do is I am going to move the screen so that we get the image of the candle on the screen. Now if I bring it closer, you will be able to get an image. So I am moving the screen, still we can't see the image, still not, and this is a far away object. So now I see the image. So students, you all can see the size of the image. It's very much smaller than the flame. So that is a diminished image. And you can notice it's upside down. That means it's an inverted image. And since we get it on the screen, that is a real image. So when the object is far away from the concave mirror, we get an image that is real, diminished and inverted. Now I will be moving the candle towards the mirror. So little by little I will move it. Now it is at the 0 mark. I'll bring it up to 10. Here you can see the size of the image increasing a little bit more. So as the object moves closer to the mirror, the size of the image increases. But still it is real because it's on the screen and it is inverted. Now let me bring it a little bit more closer. Now the distance between the object and the mirror is 30 centimeters. So here again you can see the size of the image has increased. Again if I bring it closer, now this is at the 30 mark. That means the distance between the object and the mirror is 20 centimeters. That is double the length of focal length. Okay, so here students, now you can see the image forming on the screen at the same point as the candle. That means the image is on C, double the focal length, or what we call as the center of curvature. It's still upside down, but observe the size, same size as the flame. So we get a real image, same size, inverted on C itself. Now I bring the object even more closer. Can you all see the image becoming a little more larger? Still it is real and inverted. Then I bring it to the point where we have the focal length. So now the object is between 10 centimeter and 20 centimeter mark. That is between the focal point and center of curvature. So to get a clear image, I will move the screen a little behind. Now you can see a more sharper image there. Can you see the size of the image? It's larger, so that means it's enlarged. Still it is upside down, so it's an inverted image and we can get it on the screen, so it's still a real image. Real, inverted, enlarged image when the object is between F and curvature. Then I bring it to the point where the distance between the object and the mirror is 10 centimeters. That is the focal point. Can you all see an image on the screen? No, we can't see an image on the screen. Why? The image forms at infinity. Even if I move it here and there, we will not see the image. So that means image of the object placed at focal point forms at infinity. So we can't see it. Then again I bring it even more closer to the mirror. Now also if I bring the screen closer or take it far away, you cannot see the image. So this is a point where the object is between the mirror and the focal point. That image is not got on the screen. So it is not a real image. Now if I turn the mirror towards you all, can you all see the image clearly? What do you see there? Do you see a larger image? Yes. Is it the same direction as the flame? Yes. So that means it's an enlarged upright flame, but you can't get it on the screen. So it is a virtual image. When the object is between F and the mirror, focal point and the mirror, the image is virtual, enlarged and upright. So that is the image that is formed by this concave mirror. So students, you have seen the different types of images that were formed by the concave mirror. You can see the parallel rays that are coming towards the convex mirror. They get diverged and get reflected away from the mirror. A ray going through the focal point gets reflected parallel to the primary axis. Here you can see, students, a light ray coming towards the center of curvature reflects back in the same path. Okay, students. So now we are going to observe the image formed by a convex mirror. So first I will show you the convex mirror. Here you can see this is the non-reflective surface. This side is the reflective surface. So we have it as a convex mirror because it's curved outwards. So now I will place it in the stand, and here I will place the mirror somewhere away from the candle and try to see whether we can get the image on the screen. So without moving the candle, what I will do is I will bring the mirror close and take it far away. You can see when it is moving also, you cannot get the image on the screen. So from this observation, students, you all can understand that we cannot get the image formed by a convex mirror on the screen. So what can we do? I will move the candle here, and if I hold the stand, the mirror here, can you all see the image? So that you can observe it easily. Now you can see when it is close, you can see the image in the mirror. What type of an image is this? It is the same direction as the object, so it's an upright image. And is it the same size or smaller or larger? You can surely see that the image is smaller than the object. So it's a diminished image. And we cannot get it on the screen, so therefore it is a virtual, diminished and upright image. Here, students, I move the mirror, convex mirror, backwards, that is far away from the object, going away from the object. Still, what do you see? The same type of image, smaller than the object, so it is a diminished image. We cannot get it on the screen, so that's a virtual image. And it is in the same direction as the object. Direction of the flame and the image are the same. So that is an upright image. So from this activity, now here you can observe that irrespective of the distance between the convex mirror and the object, that is the candle here, always you get a virtual image which is diminished and upright. So now we are going to observe how light refracts through a block of glass. So as you know, around the block of glass, that is on this side and this side, there is air. That is a rarer medium, whereas the block of glass is a denser medium. And you know, when light travels from one medium to another, the path of light changes. That is what we call as refraction of light. So to do this activity, I have already drawn the outer line of the glass block, and here I have drawn the incident ray, the ray that is going to fall on the block of glass. So that has been marked here. What I am going to do now is I am going to put 2 pins on the incident ray and then find the refracted ray. So here I'll put 1 pin and along the same line another pin. And then what should I do? I have to look from the other side and place the 3rd pin along the line of the incident ray and another pin along the same line. So now I have marked this is the incident ray that will refract through the glass block, again there will be a refraction at the glass air surface, and here is the emergent ray. That is the ray that is going to come out of the block of glass. Now I can take out the block of glass. I will mark the 2 points anyway that is visible to us. Then we have to connect the 2 points so that it touches the block of glass. So I can remove the other pins as well, and when I connect the rays, here you can see this is the incident ray. Then if I connect these 2 points, that will be the refracted ray, and here at the point where you get the interface, where the incident ray and the refracted ray touch each other, we have the normal, again here the other normal line. So here this is the incident ray, this is the refracted ray, and that is the emergent ray. And if you observe closely, you will see that the 2 rays are parallel to each other. If I demonstrate that with a ruler, here you can see these 2 rays are parallel to each other. We can also confirm this type of refraction using a laser beam. Okay students, so now here you can see the incident ray. It goes through the block of glass, that is the refracted ray, and again you can see the emergent ray. So by using the laser light, we can confirm that the light refracts through the block of glass. So here students, I have parallel rays going through the convex lens. You can see the middle ray going through the principal axis, the other rays going parallel to it, and you can observe that they focus on one point. To make this more clear to you all, I will push the lens and the laser beam to a side so that you can observe it more clearly. Now here you can see that all the rays, the incident rays are all parallel, but they all converge on one point. That is the focal point of the biconvex lens. So now I am going to do an activity to find the focal length of a biconvex lens. So for that I have a screen already prepared for us so that we can get the image, and you know if the image falls on the screen, it's going to be a real image. And here to find the focal length, we have to get the image of an object that is far away from the lens. So what I have done is I have kept the screen so that we can focus an object that is outside the window. So here first I'll place the biconvex lens. You can see it here students. Both sides are curved outwards. So it's a biconvex lens. I will place it in the holder, and then now I will try to focus the image onto the screen. I have to move it so that we get a very clear image. Now we have a clear image. Just to make sure that's the most clear one. So here I have the clear image. So we have the clear image of the plant that is outside the window. And here on this stand I have points marked here and here so that it's easy for us to measure the length between the mirror and the screen. So now what I am going to do is I will measure first. It is about 8.8. So here you can see this is the marked point. So when I hold the ruler you can see it is about 8.8 centimeters between the screen and the biconvex lens. So that is the focal length of this biconvex lens. So students, when I send a ray through the principal axis, you can see it's going straight along the principal axis. But when I turn it at an angle, can you all see? What can you see? Although it's coming parallel to the principal axis, you can see that the ray is changing path. It is getting refracted. The same way, if I push it to the other side of the principal axis, although the ray is coming parallel, incident ray, but the refracted ray is at an angle. But if I place it in the middle, you can see that the ray is going straight along the principal axis. So that is the optical center. Through the optical center, if we send a ray at an angle, now here again see the ray is getting bent, that is refracted. But if I send it at an angle through the optical center, you can see it going in a straight line. Same way from the other side also, if I send it through the center at an angle, that is the optical center, the incident ray and the refracted ray are same. But if I turn the angle, you can see the ray is getting bent. So this point through which the rays travel without changing the path through a biconvex lens is known as the optical center. So again here you can see the ray traveling without changing path. So that is through the optical center. So now we are going to observe the images formed by a biconvex lens. Now for that I have the screen here, the lens, and I have placed the candle very close to the lens. That is between the lens and the focal point. Can you all see an image on the screen? No, we can't see a clear image even if I bring the screen closer or take it away, still I don't see a clear image. So that means when the object is between the lens and the focal point, you cannot get the image on the screen. Now I will move it around. Now you can see students, I have kept the candle very much closer to the lens. So how do you see the image? It is larger than the object, so it's an enlarged image and it is in the same direction. So that means it's an upright enlarged image. Since we can't get it on the screen, it's a virtual image. So when the object is between the lens and the focal point, we get an image that is upright, enlarged and virtual. So after that, if I move it a little away, when the object is at the focal point, the image will form at infinity. Then also we can't observe the image. So now I will keep it somewhere far away from the focal point. Then you can see there is an image forming on the screen there. And when I move it away, you can see the image becoming smaller, and also you can observe that it is inverted upside down. And since we can get it on the screen, it is a real image. So when the object is away, when it is between f and 2f, you get the image that is diminished, real and inverted. And when I move it a little bit more backwards, when it is exactly on 2f, then of course you will be able to see the image as the same size but inverted, and it is a real image because you can get it on the screen. So when I move the candle away from 2F, then you can see the image becoming smaller. It is inverted, but it is real. So if I take it further away, you can see it's even more smaller, but still it is inverted and it is real. So those are the types of images formed by a biconvex lens. So here students, you can see this is the laser beam. I am going to generate the laser from there. The mirror, plane mirror is set here. You can see the right angle prism kept and the biconvex lens, and again we have another plane mirror there. So here the light ray that is coming and getting reflected by the plane mirror will go through the prism. It will get refracted. Again it will be refracted by the biconvex lens and it will be reflected by the plane mirror here. So it will travel back in the same path from where it came. Now we will observe that. So students, you can observe the ray coming from the laser pointer being reflected by the first plane mirror, going through the prism, then getting refracted by the biconvex lens and finally being reflected by the plane mirror again. So it is turned back in its path. Just to confirm to you all that the ray has been sent back in its path, if I move this mirror, you can see reflected ray going in a different path. If I move it more towards this side, again you can see the reflected ray. But when I adjust it to the correct position, you can see that it is only one ray that is going back in the same path. So here we have parallel rays going through the biconcave lens. You can see this is a diverging lens. So the rays get diverged, but if you extrapolate the rays, they all meet at the point and look as if they are emerging from one point. Now we are going to observe the images formed by biconcave lens. So here I have the biconcave lens placed on the stand or the lens holder and the candle is the object. Now I will try to move the object and lens are very much closer. Can you see an image? No. But when I move it around, I change the distance between the candle and the lens, still you can't see the image on the screen. So here the biconcave lens never forms a real image. So we cannot get it on the screen. So students, now we saw that we cannot get a real image, that is an image on the screen with a biconcave lens. So now I will place the lens behind the object. You can see the candle here, that is the object and the lens is behind it. Now do you all see an image? Yes. What type of an image is that? It's smaller than the object, that means it's diminished and it is of the same direction, so it's an upright image as well as you can't get it on the screen. So therefore it's a virtual image. Now I will move the lens slightly away from the candle. What do you see? The same type of image. Upright, diminished and virtual. So that means the biconcave lens always forms an image that is upright, virtual but smaller than the size of the object. It is diminished.